Right, hello A2 students. This is feedback on KA3 acids, bases and buffers. Wasn't done too badly on the whole, I'm glad to say. So I'll just go through each question and obviously try and give you some tips on how you should have answered them. So the question 1, straightforward, acid 1, base 1, acid 2, base 2, but a number of you did make simple errors because conjugate base pairs, they go together. One can be converted to the other by loss or gain of a proton. So here we have the acid, which is obviously donating the proton. Here we have the base one, which is the equivalent conjugate base, because it can accept a proton, and then vice versa with the other two. So some of you made a simple error there. Question 2, this is just asking for a Ka expression, and a number of you made a mistake by giving the Ka general expression rather than the expression for phenol. So it specifically says phenol, so this is obviously what you should have written. Calculate pH. Well, I think most of you did this okay, actually, I'm glad to say, because obviously we're just rearranging the equation for H plus, for H plus squared, and then the square root. We're making the assumption, obviously, that our conjugate base is the same concentration as H plus, which is why we can go via the squared root, and then the square root of the value, whatever it is, gives you the concentration of H plus, and then our pH minus log H plus gives 5.59. Make sure you always record pH to 2 decimal places. It's really important. Okay, question 3. Few people made mistakes here, not understanding what this titration curve is showing you. Okay, so this vertical point on the graph is telling you here the volume of sodium hydroxide that was required for this neutralization to occur. So it's 22 cubic centimeters, you can see here, and any indicator that you use for this titration would have to fall within the pH of this vertical portion of the graph. Okay, so yes, I think most of you got this right, but some people didn't. So when you're asked about measuring pH continuously, you can't use a pH paper or universal indicator or anything like that. It has to be a pH. Now you either say pH probe plus a data logger, which is what you used when we measured pH, or you use a pH meter, which basically has everything in one instrument. So it's pH probe plugged into a data logger or pH meter. Okay, so you had to use the graph because you needed to get the volume of the NaOH here to determine the unknown concentration of the acid. Yeah, so your 22 cubic centimeters came from the graph, so we could work out our moles of NaOH. We know the ratio is 1 to 1. Well, I mean, you're not given it, so you would need to, if you're not sure, write a quick equation. 1 to 1 ratio, so we know how many moles of acid are in the 25 cubic centimeters, and then it's a straightforward conversion to concentration. Okay, and this is obviously using the vertical portion of the graph to identify the indicator that you would be able to use for this titration. Yeah. So if we look at our graph, it needs to be between pH of 6 to around about 11, so it's got to fall within that range, and the only one that does that is the brilliant yellow. This was just writing an equation and balancing it. Yeah, okay, maybe not the easiest equation to balance, I don't know. If you look at calcium first, that would be the first thing I would balance here. And what have I got actually? I haven't. Oh, hang on a minute. Yeah, going back to this equation, I've made an error here. I haven't put the 2 in front of the calcium sulfate, which I just realised when I was looking at it. So this should actually say 2 CaSO4. So balancing the calciums, as I said, you need 3 of them. And then I would balance the polyatomic ions, the phosphate, and then the sulfate, and then the hydrogen. Okay. Okay, so question 5. Ask for the name of KW, which basically that's just something you need to learn, and you also need to know that this expression is KW. They're 2 very straightforward, easy marks there. Part B, okay, so you're given some information and then you're asked to calculate the concentration. So I would straight away scribble down my equations here just to remind myself what I'm going to be doing, because the information you're given in the question indicates that these are the equations you're going to use because it was a titration. So we know our concentration of hydrochloric acid and we know our volume of hydrochloric acid. We've got a volume of the water, so obviously that's what we're going to use. The important information here really is that there are 2, for every 1 mole of calcium hydroxide, you've got 2 moles of OH minus. Okay, so you need to factor that into your calculation. So you work out your moles of HCl, look at the ratios 1 to 2. So we divide the number of moles of HCl by 2 to find the number of moles of forgetting what I'm doing, calcium hydroxide, and then we can work out our concentration. Okay. Okay, part C. Right, okay, so then we analyse the water. Again, we're given some information and we're given a concentration of calcium hydroxide. And we're given the equation of calcium to hydroxide. So this is the question, the part of the question where you need to recognise there are 2 hydroxide ions. If you didn't, then obviously you wouldn't have had enough moles in your calculation. So you're going to use the KW expression, yeah, rearranged for H+, okay. Then we need to work out our concentration of OH minus, and like I just said, you're given the concentration of calcium hydroxide. Now, because it's a strong base, it totally dissociates, but because for every 1 mole, as I just said, of calcium hydroxide, we have 2 moles of hydroxide ions. We need to multiply that value by 2, and some of you didn't do that, so you lost a mark as a result, but you did gain 2 marks if you forgot to do that bit. Okay, so yeah, rearrange the equation then for H+, work it out, because KW is a constant, yeah, which you must know. Okay, so now we've got our concentration of OH minus, then we can find out our pH. Once we've got that, concentration of H+ gives us our pH. So again, make sure that you've recorded that to 2 decimal places. You lose a mark if you only record it to 1 decimal place. Okay, so this last part of the question, a little bit of confusion with some of you, because this is saying after further treatment, yeah, the drinking water, the OH minus concentration was 100 times greater than the H+. But we're not talking about the previous concentration of H+ here, yeah. So this is related to KW, the KW expression, yeah, and we've got 100 times more than our H+, yeah. So we rearrange the equation for OH minus, yeah? And again, we're making this assumption that H+ and OH minus are the same, so we can effectively call it H+ squared. If you go through my calculation here, hopefully it's obvious how we come out to a pH of 8. Yeah, once you've got your equation the right way round, you shouldn't have any problem with it. Okay. Question 6. Okay. So this is a buffer calculation. So you're going to need the buffer expression, which you really need to know. You know, it comes straight to mind as soon as you see a question about a buffer, and it's asking you to determine something to do with it. Then you're going to need this expression, which, remember, it's been rearranged. So we've got Ka on this side, which means we have concentration of the acid up here, concentration of the conjugate base on the bottom. So it's the opposite way around, obviously, to the Ka expression. Okay, and the information we're given in the question, I've underlined it, which I would do if I was answering this question in an exam. So we can work out our concentration of H+, it's 10 to the minus pH. So there we've got that. Once we've got concentration of H+, we can find the A-, which is basically what we're being asked to do. We need to determine the concentration of sodium phenoxide. That is where your conjugate base is coming from, isn't it? Remember how the buffer works. So the sodium phenoxide will be producing your conjugate base. So we rearrange the equation for that, for A-, plug in the values that you're given. You're given Ka. You are given the concentration of the acid, and you've just worked out concentration of H+. Okay, and then there you go. Do the calculation. Okay, question 7, very straightforward. I mean, these are just reactions of acids with various substances. You know, with a metal, we always get hydrogen plus a salt. With a carbonate, we always get carbon dioxide plus water and a salt. With a base, we get a salt plus water. So really, no one should have got these questions wrong, but some of you did. Ethanoic acid and sodium hydroxide is exactly the same as any other acid and base. You get your salt plus water. For some reason, some of you seem to be confused. Just because it's an organic acid, it's still, if this was HCl, you wouldn't think anything of writing NaCl, so i.e. the metal ion plus the conjugate base. Well, here's your conjugate base and here's your metal ion, that's all. And then ethanoic acid and calcium, again, it's just an acid plus a metal, and a lot of you put H+ here for some reason. You're going to get hydrogen gas, and again, you would get the salt, but you would have to have 2 of the conjugate base with each metal ion, because calcium forms +2, doesn't it? So very straightforward. I mean, if you got a question like that in exam, that would be a real result. 5 marks. So really, really nothing difficult at all. Okay, question 8. Yeah, so question 8 quite long because there's I think 3 parts to it. So, but the first part of the question, no one should have had a problem with, but a lot of you didn't put in an equilibrium sign, which I can hardly believe. Okay, the dissociation of a weak acid obviously is an equilibrium, and if you put an arrow there, then you didn't get that mark. Okay, part B, being asked to calculate the pH of the solution, which again is very straightforward because you're given H+ concentration. But what a lot of you didn't do to get the second mark was to give a reason why the pH scale is more convenient than a concentration of H+. All you had to do was say that pH is, gives a more manageable number, or, doesn't use small powers of 10 numbers or something along those lines. Okay. Again, expression for Ka for methanoic acid. So it has to be for methanoic acid, not HA over H++ times A-. So it needs to be specific. Calculate Ka and pKa, straightforward enough with the information that you're given up here, obviously in the question. H+ squared, that assumption that we've got our, conjugate base and H+ is the same concentration. Put those numbers in. There's Ka, and of course pKa is minus log of Ka. So that's very straightforward. And I think a couple of you didn't do this second part, so you missed out on a mark there. Yeah, this one caused a bit of a problem. I don't know whether some of you just thought when it says estimate the percentage that have dissociated that you just had to guess, but that's not the case. You had to kind of make an estimate based on information that you've been given. So we know our concentration of H+, we know our concentration of our acids, so we can work out how much of the molecules have dissociated. Okay, so 10%-ish. Okay, part C, buffer solution question again did cause problems. This question was not well done. Part C of this question was not well done. Only a couple of students did it properly, I think. So again, you've got your buffer equation, which you should know. You've got all the equations on the sheet, the ones that you need to know off by heart. We've got information that we can put in. Now these values that you're given here, you've got told 2.35 times 10 to the minus 2 moles and 1.84 times 10 to the minus 2 moles, and they are in 1 cubic decimeter. So that is the concentration, isn't it? 2.35 times 10 to the minus 2 moles for dm cubed. Yeah? Okay, so you don't need to do any calculation as such, so you just put them into the equation, calculate concentration of H+, and then work out the pH by taking the minus log. So some of you are probably kicking yourself if you actually realise how easy that calculation was. And then this one, obviously a little bit more to it, and so this is the kind of extension part of the question, that we're asking what's going to happen to the pH if we add some hydrochloric acid to this buffer solution. So we need to work out how many moles of hydrochloric acid we are adding, which is very straightforward because you're given a concentration and you're given a volume. Okay, so that number of moles is going to react with that number of moles of your conjugate base. This is basically the theory behind this, isn't it? So if we have that many moles of our conjugate base, we're going to take away that many moles of it because it will have reacted with our acid. Yeah, so that's going to be our new concentration for our conjugate base. And on the other side of the equilibrium, we are going to add that many moles of acid to our original concentration, which was 2.35. So we're going to add the 2.35 to 5, so we're going to end up with 2.4 times 10 to the minus 2 moles of acid for dm cubed. Okay, so those new values go into this the same buffer calculation. Your 1.6 times 10 to the minus 4 comes from up here where you worked it out. Yeah, your pKa. Sorry, your Ka, not pKa. Sorry. Ka, yeah. So that goes into the equation here. Your new concentrations, which obviously have changed because you've added some acid to this buffer solution. So we work out our concentration of H+, and then we work out the pH of that by taking the minus log. So 3.67, and as you can see, it hardly changed from 3.69. Which is what you would expect of a buffer solution. Okay, that's it really. I will speak to you about it tomorrow or whenever I next see you after I have written all the feedback on your work. Bye for now.